topic of my today's speech is mathematical issues of different schemes for atmospheric boundary layer equations. At first, I'm going to start from the importance of the considering problem. All we know that there is a problem with the ecology in Kazakhstan, especially air pollution. So in order to consider this problem, we will consider the model of atmospheric boundary layer in order to simulate and predict the spread of harmful substances in the atmosphere. So the model of the, it's a bit confusing when there is a little bit, oh, it's okay. No, эхо просто мешает. So all we know that this model consists of several equations, and this model arises from the considering of movement of the air in the atmosphere that occurs with the continuous distribution of the pressure. So uneven distribution of pressure is caused by the process of heat exchange in the atmosphere, and the heat and the moisture exchange represents the main factors determining the weather and the climate. So by improving and changing this model, we can apply this model also for consider environmental problems too. So there are a lot of work that are devoted for the for this topic, such as the works of Marchuk, Penenko, Alayan, Arguchintseva, and so on. And there is a model that's called Gaussian model that is also will be useful to consider the propagation of gas and particles from point resource. So here's the considering works. In Kazakhstan, there are a lot of scientists who works who are engaged in creation of geoinformation systems in the field of ecology, like Zagarin, Danaev, Isakhov, Abdibekov, Rahmetulina, Malgazdarov, and so on. And the works of Smagulov, Danaev, Zhmagulov, Timorbekov are devoted to the mathematical substantiation of the numerical solution of problems that are on the basis of considering system, as well as the works of Muhammadjan, Futilbay, Smagulov, Timorbekov, and many others. So let me just introduce my considering model. This model consists of 6 equations. First 3 equations are the equations of motion. Fourth equation is the continuity equation. Fifth, heat inflow equation. And the 6th is the model of the transfer and the transformation of impurities. So here, t is a time, x, y, z are the Cartesian coordinates with velocity vector with the components u, v, omega, p is the pressure, lambda convection parameter, s stratification parameter, mu x, mu y horizontal turbulence coefficients, nu is the vertical turbulence coefficient, theta is the potential temperature, L is the Coriolis parameter, Pq is the proportion of the concentration of harmful substances, Fq describes the source of substances, alpha q, beta q coefficients arising from the equations of transformation of impurities. So the following initial and boundary conditions will be considered for this model. First one, for the case when t is equal to 0, it will be initial condition. So the next x equal to 0, x equal to capital X are the boundary conditions for the x-axis. Fourth, fifth are for the case when y equal to 0, y equal to capital Y, and the last 2 for the case when z equal to h and z equal to capital H. So it will be for z-axis. So here h is a conditional high, x, y are the dimensions, pq0, pqh are the proportion of concentration of matter q, theta q is the temperature at the level of roughness, au, a theta can be determined by these given fractions. H is a height of the surface layer, or another, it will be better to say level of roughness. Theta H, theta 0, and psi-u, psi-theta are determined as in work 24. U1, V1 can be determined based on meteorological conditions. And for theta and the phi q, they will be taken into account that on the surface layer, there will be interaction of impurity with the underlying surface. So in order to solve this problem, we will move to dimensionless form using these notations for the given elements. And after moving to dimensionless quantities and dividing all terms by this given term, we will obtain the following dimensionless equations of motion in the form of 8, 10. And here, the components of the equation. D is a dimensionless characteristic of wind deviation from geostrophic, and the Reynolds T is a dimensionless number of turbulent exchange. So dimensionless heat equation would take this form. Dimensionless equation of impurity transfer will take this form. The form of 12 after moving to dimensionless quantities and dividing equation by this term. So here we'll consider the following grid in order to solve our problem. So velocity components u, v, omega will be considered correspondingly, respectively, in the grids omega x, omega y, omega z. Theta temperature will be also considered in grid omega z, and the harmful substances phi q will be considered in the grid omega h. So finite difference scheme will be presented for equations of motion in the form of 13, 15, for the continuity equation in the form of 16. Heat inflow equation will be presented in the form of 17, where convective elements of the equation of motion will be presented in the form of 18, 19, and 20. So for heat equation, there will be convective element presented in the form of 21. Diffusion terms for the velocity components of the equation of motion will be presented in the form of 22, 24, and for temperature it will be presented in the form of 26. Oh, sorry, 25. So different scheme for the impurity transfer and the transformation equation we presented in the form of 26, where convective and the diffusion terms will be presented in the form of 27, 28. And the coefficients alpha and beta can be determined in this way. I will clarify these moments after numerical implementation algorithm. In order to solve this problem, we will consider the splitting by the physical processes. At first, we will determine the speed on the step n+1/2 using the equation 29. After that, after determining these elements, we will define the pressure field taking into account that divergence of the velocity vector should be equal to 0 using equation 30. And after that, we can determine the speed, velocity on the step n+1 using the equation 31. After determining the velocity, we can find the temperature using the equation 32. And for the transfer and the transformation equation, we can also use splitting. Using the equation 33, we will consider at first the transfer of the fractions of the concentration of harmful substances. After that, we will consider transformation using equation 34. And I will clarify the moments that are related with the coefficients alpha, beta. There exists such an equations that are called equations of chemical kinetics. They are useful in order to determine the coefficients of the speeds of the actions between the reactions, different chemical elements. And for example, if we will consider the element HO3, the chemical equation for this substance will be presented in the form of 35, where alpha beta coefficients will be correspondingly, I missed here, equal, correspondingly will be equal to these two elements. And in the same way, we can determine its poles for several harmful substances. And the next step that we will consider is approximation of the stability of the difference scheme. At first, given equation of motion, we will integrate left parts of the equation of motion. We will integrate and divide by the H1, H2, H3, and obtain the following difference relations for equations of motion: 36, 38. Similarly, it's possible to obtain the difference relations for the right-hand side of the equation. And finally, we will obtain the following difference scheme in the form of 39, 41. Where these coefficients AI plus 1 JK and many others can be determined as 42, 43, and so on. Continuity equation will be presented in the form 44. Different scheme for continuity equation will be presented in the form 44. The following initial and boundary conditions will be considered for this different scheme in the form of 45. And for unambiguous determination of pressure, we require that the equality 46 be fulfilled. And here takes place the lemma for grid functions u, v, omega from the given grids that satisfies the conditions. 44, it's the condition that divergence of the velocity vector should be equal to 0, and the condition 45 is the initial and the boundary conditions. If these conditions will be satisfied, then equality 47 takes place, equality holds. It will be useful when we will consider the stability. So we will consider the norm of the velocity vector in the form of 48. This is the discrete analogy of the norm in L2. So multiplying the difference equations 13, 15 respectively by the given elements, and considering the summing by the points of the given grids, we will obtain the following basic energy inequality in the form of 49, where dH can be determined in the given way. So here, clarification of the elements of the dH. Here we have L2H, so it will be equal to the given elements. This scalar product between the and L2 to the dH, we will obtain 51. After that, if we will use the Young's inequality and the boundedness of the coefficients A from below, we will came to the inequality of the form 53. Or in a vector in 54, gradient of the vector velocity can be determined as given, and the C1 is equal to this term. Now, in order to estimate this summand, we transform the summand SH as follows. Let SH be equal to this, and after adding and subtracting these elements, V and UN, we can split it into these two brackets in the form of 55. After that, if we will apply Young's inequality, then we will get the inequality in the form of 56. In the vector form, it will be presented as 57. So using previous considered lemma, we can consider the equality 58. And after using Cauchy-Bunyakovsky inequality, we can estimate this term as in 59. So here, this value is estimated as follows, as in inequality 60. Inequality 60 and 61, I have considered from the work of Ladezhenskaya. And C3 can be determined by this. And finally, from this, we will have the inequality of the form 62. So using that fact that gradient of the velocity vector is non-zero and this inequality, we will get the inequality of the form 63. And we require that the following conditions be met. This term will be non-negative and this term also will be non-negative. Then we will get the inequality 65, which allows us to evaluate the velocity vector and the gradient of the velocity vector. So as long as the coefficients at the gradient of the velocity vector is non-negative, we have inequality 66. And after some transformation, we will get inequality of the form 68. And from 65, we derive that taking into account this 68 inequality of the form 69. So it means that we have the stability of the considered difference scheme by its initial condition and the right-hand side. So let's consider the convergence of the finite difference problem. To study the convergence of the solution of the finite difference problem to the solution of differential problem, we consider the finite difference relation for the equations of boundary layer of the atmosphere of the form 3941. The error of solution of the differential problem 1.5 and the difference scheme 131726 is defined as follows. We will introduce such indentation for the components of velocity vector and for pressure. So substituting these denotations into the difference scheme 1316, we will get such a difference scheme for error. Where error approximation of the difference scheme 131726 on the exact solution of differential problem 1.5 is defined as 78, and it has approximation of second order by h and the first order by tau according to work 22. Convective terms for the components will be written in the form of 7981 for the equation of motion. So here will be considered initial and boundary conditions for this problem. Such an initial and boundary conditions be considered for error problem. Such a nonlinear terms arises when we will consider error problem. And multiplying the difference equation 7477 respectively by the given terms, then summing of the grids, given grids, we will obtain energy inequality of the form 82, where the elements dph, svh can be determined as 53 and 54. So let's consider terms that are absent in the energy inequality of the form 49 that we'll consider in the case of stability. Using the summation formulas in parts and the limitation of the components of the velocity vector Vn, and considering the averaged values Vn at neighboring nodes equal, and applying Young's inequality, we obtain inequality in the form of 85 for error. So from here, if we will write the previous thing in the vector form, we will obtain such an inequality. By substituting it into our previous energy inequality in the form of 52, we will have the inequality in the form of 56. Substituting estimate for this term, we will have inequality of the given form. Denoting that A will be equal to 1 and B will be equal to these elements, we can rewrite our previous inequality in the given form. Considering that A will be greater or equal than B, it equals that this term will be non-negative. And we will put such a condition that this term and these terms will be positive and this term will be non-negative. And taking into account non-negativity of the third and the fifth terms, these terms will be non-zero because of these conditions. So we will get inequality of the given form, where C5 will be defined as follows, as presented below. So considering that A is equal to 1, we will have this inequality, and reasoning similarly as in previous case for the problem 74-78, we will get an estimate of the given form. Further, considering that the error approximation has approximation by a second order approximation by H, we will have such an estimation, which proved that the convergence of the solution of the difference problem 13, 17, 26 to the solution of the differential problem 1, 5. So here arises a theorem. Let these conditions will be fulfilled, then the solution of the difference scheme 13, 17, 26 is stable, and the converges to the solution of differential problem 1, 5 at a rate determined by the inequality as presented here below. So here is the numerical results. We have considered the numerical implementation for the city Uсть-Каменогорск, and calculation were performance for the area 35 by 35 kilometers, and surface layer height of 3,500 meters. And the numerical implementation was performed based on the given data. In table 1, these terms, these data were taken correspondingly for the city Uсть-Каменогорск. And here is the spread of harmful substances CH2O. Here for CO, CO2, SO2, NO3, H2SO4, and there were considered a lot of them, but I decided to show this only these harmful substances. And the conclusion, based on the considering model, software is being developed within the framework of the program. Developed software makes it possible to access a degree of pollution of the air basin of an industrial city, taking into account the transformation of the harmful substances and the geographical location of the city. There are also, during my investigation of my dissertation work, there also can be considered, there also will be considered packages WRF SILM that also based on such a different system of differential equations and simulates meteorological conditions and the spread of harmful substances. And after obtaining the results from these packages too, the results of my model and results of these packages will be compared. Finally, there will be constructed game information system that will help to predict the spread of different harmful substances in industrial cities. And my future aim is to obtain the estimation for pressure gradient of the pressure and for diffusion term of the given Navier-Stokes equations for the equation of motion. So that's it. Thank you for your attention.